Alright guys, in this video we are going to cover 3.7 equation solving and modeling. This video is going to be focused on solving, whereas part B is going to be focused on modeling. So whichever one you need to view, make sure you watch the correct one. This is the first part. We're going to just talk about extra ways to solve equations with exponential and logarithmic equations. We've done some questions, but the questions examples need to get a little bit more challenging so we really get a good feel for how to solve these things. And what we're going to do is add an extra property in here to try to help us with solving them, making it a little easier when the problems get ugly. If you have a situation where you end up, if you're able to say that some number to a power equals that same number to a power. So if these bases are the same, then what you're able to do is just not bother with the bases and just set the exponents equal to each other. And you get a similar idea when you use logarithms. If they have the same base like this, log base b of x equals log base b of y, you're able to get rid of the log part and just say that x and y are equal. So it's just a really nice way to kind of simplify problems when that is applicable. Okay, so let's get into these two examples. You're going to see down here example 1, we got part A and part B. Now if you're having trouble reading some of this, I know a little bit of it's kind of small, so like on part A, this little exponent right there is saying x over 3. That's your exponent, x over 3. So please make sure that you have the correct thing before we get started. All right, so here's what I'm going to suggest on this problem. All right, you might be looking at it and saying, well, that's great that you just gave me that property. That seems real simple, but this problem does not look like that. And you're right, it doesn't look like that, but we can make it look like that. It's just going to take a few steps to make that happen. So if you look at this one, we've got 20 times 1/2 to the x over 3 power equals 5. Now, the first impulse many people have is to multiply 20 and 1/2. But because of order of operations, PEMDAS, you can't do that. Because 1/2 is being raised to a power, you can't just multiply these values to begin with. So what we're going to do instead is we're going to just work on getting things away from x. Remember, x is in that exponent. So let's start by trying to get things away from x. I'm going to start by dividing both sides by 20. And what happens is that cancels here on the left. So really I have 1 over 2 to the x over 3 power. And then 5 over 20 reduces down to be 1/4. So we're not quite there, but this is already starting to look a little bit nicer just in that one little moment. So this is 1/2 to the x over 3 power. This is 1/4. However, 1/4 can be written as 1/2 raised to the second power, right? If you squared 1/2, 1 squared is 1, 2 squared is 4, 1/4. So that's the same thing. And so at this point, now I do have it set up. It only took a couple steps, but now it does look like that property we had. And I can just drop those bases and say x over 3 equals 2. Last step, multiply both sides by 3. You end up with x equals 6. All right, so there was one problem. Let's do another one that's kind of similar. This one might feel a little bit more simple because we don't have all those fractions, but there's some other things you got to look out for. So this is 9 to the 2x power, and then we have 27 to the x plus 2 power. I don't know about y'all, but when I look at the numbers 9 and 27, to me, it's like, what do they have in common? Well, they're both multiples of 3. And not just multiples of 3, they're also both powers of 3. 9 is the same thing as 3 squared, right? So really this is 3 squared, 9, to the 2x power. And over here, 27 can be written as 3 to the third. And that's still to the x plus 2 power. Then you just got to remember your exponent rules from Algebra 1. This is 3 to the 2 times 2x, 3 to the 3 times x plus 2. And now I'm able to drop those bases. Really, 2 times 2x is equal to 3 times x plus 2. That's way more simple at this point. We got 4x if you multiply that out, and then over here, distribute your 3. 3x plus 6. Subtract your 3x, we get x equals 6. Again, we got, that's just a coincidence, guys. The answers are not always 6, all right? So that just kind of happened. But yeah, those are how we can solve exponentials. It's not the only way to do it, but it is a way, and it is something that can help make problems a little bit easier, more manageable. All right, next thing, let's look at solving logarithms. So we've got 3 of these here that we're going to try to solve. Okay, so y'all go ahead and get those written down so that we can go through it. The first example you're going to see here is that example 2 part A. That example is very similar to ones that we have done before. Back in section 3.4, we talked about how you can solve logarithmic equations a little bit already, but this is just kind of like expanding on that. Now, example 2, I'm going to work the same way we did back then, so we can kind of compare the differences. But with this logarithm, I see 1 log in the problem, which simplifies things quite a bit. If I only see 1 log in the problem, it makes things really nice. What I can do is I can actually change this to exponential form to solve it. Right now it's in logarithmic form. But in order to do that, I do need to know the base of my log. It's the common log, which is base 10. And so we're going to write that in exponential form by taking the base of that log and making that the base of my exponential. Remember that a log is equal to an exponent from the exponential form. So this 2 becomes a 2, a squared on my 10. And then that is equal to x squared itself. Now here's the first thing people will do is they'll just say, all right, well, my answer is 10. But the problem that we have with that is you're actually missing part of your answer. So I want you to remember how this would work if we worked it fully out. 10 squared is 100. And if I were to square root this on both sides, you got to remember that you end up with both a positive and a negative answer. We get plus or minus 10 to be your x. We are going to have to look out for extraneous solutions. So you want to make sure that the values you have actually work as answers. And if you recall, we can't have a negative inside my logarithm. I want you to look back at my log. This is log of x squared. So what we got to think about is it's not that I can't have a negative answer. I can have a negative answer, but what I don't want to do is have something that would make me have the log of a negative. So let's think about plugging these in. Would that happen? If I plug in a positive 10, 10 squared is a 100, and that's a positive number, that's fine. If I plug in a negative 10, negative 10 squared is also positive 100, which I can do. So both of these are valid answers. And in some cases, you only get 1 solution, but in this case, I do have 2. There's also similar situations where you can get no solution as well. So just always be mindful of that. Go back and take your answer, plug it back in, make sure it works, because if it doesn't, then there is no solution. All right, look at part B. Here's how this one's different. It's not just 1 log. So in part A, we only had 1 log. And in that situation, I think it's really nice to be able to change to exponential form. However, this has 3 logs. And when there's 3 logs, we need to come up with something else to do. So let's figure out how can I rewrite this in a way that I can actually solve it. And that's where we're going to take it back to our properties up here. All right, if I can rewrite it to where I have a log on each side of the equation with the same base, log base b of x equals log base b of y, then I can drop the logarithms completely, and it's no longer a logarithm question. So let's see what we can do there with part B. All right, I see my equal sign over here, right? But I have 2 logs on this left side. So let's figure out how can I condense it. Well, we do have a property that allows me to take 2 logs that are being added and change it into a log of a product. That was that product property that we learned a couple sections ago. So I'm going to rewrite this, and it's going to be 1 logarithm this time, but it's going to be a log of a product. So it's going to look a little messy, but there it is. All right, let's zoom it in just a little, see if that helps. All right, now this other one, I don't want to leave it in that format. Remember, we want it to be a log on each side. This is 2 times the natural log. I don't want that. So let's rewrite this as the natural log of x to the 2nd power. Use that power property that we talked about a couple sections ago. All right, now that I have natural log on each side, remember that's log base e, so this is fine. We can drop the logarithms and just turn it into a normal algebra problem that we're used to. All right, so the logs drop off, and now I have to FOIL and solve the quadratic. So 3x times x is 3x squared. 3x times -1, -3x. -2 times x is a -2x. And then last times last, -2 times a -1 is a +2. All right, we're going to subtract this x squared over to make 2x squared. Combine your like terms in here, get -5x. We got +2 equals 0, and now it's time to factor. Everybody's favorite part of solving quadratics. Yes, you can use the quadratic formula, but this is a whole lot faster if you get used to it. All right, so what we're going to do is put what we know has to be there. We're going to plug in. And then we're going to guess and check for the rest of it. So remember that the first times first in my binomials has to equal 2x squared. There's only one pair of values I can use to make that happen, and that would be x and 2x, right? X times 2x, 2x squared. That's the only way to make that happen. Now, the other thing is I need the last 2 numbers to multiply to be a +2. And then when I combine things, we need it to make a -5. So if I need them to multiply to be a +2, I need the signs to be the same, either both positive or both negative. But because eventually I want numbers to add to make a negative, I need these numbers to both be negative. Otherwise, it's not going to happen. All right, this brings me to the guessing and the checking part, everybody's favorite part of factoring. So we're going to kind of make an educated guess. We know that the last 2 numbers have to multiply to be 2, which means it's either 1 and 2 or it's 2 and 1. And that really is my only guessing that I have to do is figure out which order to put those in. Okay? So what we're going to do is just check one of them. Let's try. Now don't put this in pen. See, I'm using a pencil myself. Let's try this pair. If I put the 1 and then the 2. Okay, well, if I do it in this order, I want us to think about what that is to FOIL it out. First times first, 2x squared, perfectly fine. Outside times outside, that's a -2x. Inside times inside, -2x. If you add a -2x and a -2x, that does not make -5x, and there's a problem. Therefore, let's swap them. We're going to swap these and make it 2 and then 1, and now check it. Remember, first was fine. Outside times outside is -x. Inside times inside is a -4x. These do combine to be -5x. Therefore, that's the right pair. All right, so again, you can use a different method. If you have one that you like better, that's perfectly fine. But this is what I use most of the time, and then I'll use quadratic formula for other things. All right, so next part, let's actually solve it. So we've got it factored. Solve each of these for 0. So we have x minus 2 equals 0, or 2x minus 1 equals 0. This is x equals 2, or 2x equals 1, x equals 1/2. All right, Now, we need to take this back and make sure that all of my answers are valid, because remember how we said sometimes you get those extraneous solutions and we don't actually get a real answer. So let's go back to what my original problem was. And we need to check, do either of my answers cause me to have a negative or a 0 in my log? So if I were to plug in a 2 for each of these, 3 times 2 is 6, minus 2 is 4. That's fine. Plug in a 2 to the next one. 2 minus 1 is a positive 1. Perfectly fine. Plug in a 2 over here. Log of 2, that's perfectly fine. So as long as it's a positive number, it's okay. Now let's plug in the 1/2 and see what happens. All right. Well, the first one that's coming to my brain, I'd rather not multiply 1/2 times 3 if I can avoid it. So this one seems easier. If I plug in a 1/2, 1/2 minus 1 is a negative 1/2. And right there, we have a problem because I cannot do a log of a negative number, and that would make me do that. So that actually can't be one of my answers. My final answer is just x equals 2. 1/2 does not get to work. Okay? All right. So we got one more example of this type, which I would like you guys to pause the video and try for me real quick, and then come back when you're ready to go over it and make sure you've got it. This question does have us do something slightly different than the last one, but it's very similar in nature. So it's got 3 logarithms, 2 on one side, 1 on the other. And but this time they're separated by a difference instead of a sum. And so that has me use a different property to begin with. I'm not going to be using the product property. We'll use the quotient property. All right, another thing is before I use the quotient property, I need to take care of this 3. I need to use that power property and rewrite this as an exponent. So we got a couple things going for us before we can drop the logs. Let's see, this is draw log base 4 of 2 to the 3rd. And over here, just rewriting. All right, now we're going to use our quotient property and rewrite this as 1 logarithm. So this is log base 4 of x over 2 cubed. I'm going to go ahead and write that as 8. And that's equal to log base 4 x plus 7. So at this point, I can drop my logs. This gives me just x over 8 equals x plus 7. And then I can multiply both sides by 8, right? Use that. Multiplying by the denominator trick. And so we end up with just x equals, distribute that through, 8x plus 56. Subtract your 8x, we get negative 7x equals 56. Divide, we get, negative 8, just like that. So here's the deal, all right? I got x equals negative 8. Now, I only got one answer. That does not mean that that's actually the answer. So I need you to take that number and double check that it's actually a valid solution. I'm going to take that negative 8, and we're going to go back to this first log base 4 of negative 8. Right there, red flag. You cannot have log of a negative. So when I plug in that negative 8, it does not work. That is an extraneous solution. And you might say, but that was my only solution. That means that there's actually no real solution to the problem. So we're going to say no solution, or you can say that null set answer. Okay? All right, if you are on level, you are done with this lesson. However, AP, stick around. We got one more example, okay? All right, here we go. One more example, AP. Whew, that barely fits. Okay, so we have 2 different functions on here, h of x and k of x. What it's asking, they've given us functions for each of them. They said, what are all the x coordinates of the points of the intersection of h and k? That should say h and k, not a plus, Okay, I just ran out of room to write the word and. So what are all of the x coordinates of the points of the intersection of H and K? So in order to solve this, we need to come up with a way to tell where these things would intersect without necessarily using a graph, right? So you could graph them on a graphing calculator, just see where they cross. But the problem is that's not always an option for us. Sometimes we don't get calculators, right? Especially in AP. So we need to be able to solve this without it. Therefore, we're going to set these two things equal to each other because that will tell me where they have x's that are the same. All right, so let's look here. We got my h of x function, which is log base 3 of 2x minus 3. And we have plus log base 3 of x plus 4. And what we're going to do is take that h function and we're going to set it equal to the k function. So that's log base 3 of 8x plus 2. All right. Now here we go. This becomes very much like example 2 part B. So what we're going to need to do is rewrite this using the product property. We're going to write this as 1 logarithm. And then we're going to multiply 2x minus 3 times x plus 4. Over here, log base 3 of 8x plus 2. And now we can drop the logs. Just becomes 2x minus 3 times x plus 4. And the other side, 8x plus 2. So the logarithms are gone, and now it is just a quadratic problem, right? We're going to FOIL this out. We get 2x squared plus 8x minus 3x minus 12. All right. Move everything to one side and combine your like terms. We got 2x squared minus 3x minus 14. And now it's time to factor once more. We love a good factoring problem. All right, next thing, break this apart into two binomials. Yes, it does indeed factor. Remember what we said earlier. If I wanted to break this apart, 2x squared, I know that this has to be 2x and x. Doesn't have to be in that order, but it needs to be that pairing. All right, now the last thing is I need the last two numbers to multiply to be negative 14. And this is a little bit trickier than the last one. One of them is going to have to be positive and one's going to be negative, but we don't know which one is which. Now, when I see the number 14 and I think of factors, immediately the first thing that comes into my head is 2 and 7. So why don't we see if I tried 2 and 7? All right, that's the first thing that comes in my head. And which one do you think would be more likely to give me this negative 3? I'm thinking the bigger number being negative, but let's just check. If I did 2x times x, 2x squared, 2x times a negative 7 is a negative 14x, and then 2 times x is a positive 2x. That does not combine to give me a negative 3. Why don't we swap them and see? Let's try negative 7 over here and then a positive 2 there. See if that makes a big difference. First times first is fine still. X times, so outside times outside. 2x times 2 is 4x. Negative 7 times x, inside times inside, is negative 7x, which does combine to give me negative 3. So I think that's the best order. Negative 7 and positive 2. And that's literally how I FOIL, or I factor most of the time. I usually don't use any of those other little methods. I just check until I got things that work. Okay, so now we're going to take each of these and set them equal to 0. So 2x minus 7 equals 0. X plus 2 equals 0. 2x equals 7. X is 7 halves. And then over here, x equals negative 2. All right, so that was fun. We have answers, but I've got to make sure that both of them are valid, right? Or that either one of them is valid, because it's possible to have no solution. So if we plug these in, 7/2, that's the same thing as 3.5, right? So if I plug that in, that would give me 7 minus 3, which is 4. That's perfectly fine. If you plug in 7/2 up here, that's definitely going to give me a positive. Plug it in here and we get a positive. So it's perfectly fine. No issues with plugging in 7/2. But what about plugging in a -2? If you plug in a -2 right here, 2 times a -2 is a -4 minus 3, -7. Right there. That one is extraneous. Does not work. Whereas the 7/2 is perfectly fine. Ta-da! All right. So guys, that is it for this video. If you made it through to the end, congratulations. And then I will see you guys in the next video for modeling. All right. Good luck.